This experiment is all about optics. We're going to use some of the latest optical instruments plus some very old instruments and put them all together in a really good experiment which has several different parts. It's not easy. Some of the sophistication is worthy of a graduate student. You'll have to do some studying on your own and decide where to stop, because if you took the time to investigate all the optics that we're working with until you understood it thoroughly, you wouldn't do anything else for the whole semester. The result is, of course, you have an intensely interesting, modern, present-day experiment. You can go into one of the professor's research labs and see this same kind of apparatus right there being used for current research. And that makes it very exciting. We're not going to start with one of the marvelous instruments of the day, what's called a diode laser. You remember what a laser does, essentially. It produces what's called coherent light. It's single frequency with a beam which travels with almost no divergence to it for practical purposes. So, for example, we can have a beam of red light, let's say like this, and go almost to the moon with it, but before it spreads out so far you can't see it. It's just very well collimated light. In our particular case, we're going to use a diode laser, it's called, and rather than explain to you what all is inside, except to say it has a diode which, when current passes through it, it generates light. And then we have a cavity with mirrors, in essence, one with a little bit of transmission, and out comes infrared light. In our case, this is about 780 nanometers. So we have a beam here beyond where you can see that goes straight out and for a long distance. It has a power of about 10 milliwatts continuous. This is right at the edge of permanent damage to your eye if you would look straight at it. Therefore, you don't want to put your eye here and look back into it. In fact, you don't even want to look at reflected light directly. So we have two ways to cope with this. We have a little card about this big with a spot on it which is sensitive to infrared light, and it changes it into visible radiation. So if I just hold the card up, put that right here, we see a spot and we have no problems. You wear a pair of goggles with this, which cuts out this light, but you can still see this light, so you can trace the beam. And it's about this big. It's a couple millimeters like this. Not completely symmetrical, but easy to observe. We also have a second strike, or a different way that we can observe the radiation. If it's too weak, or if we want some more exact thing, then can be measured with a card. We have an infrared telescope, and I'll just put it here kind of like this. It's, I'll call it, this is a telescope where you put your eye right here. I'll put up a piece of paper here, like lens tissue or something like that, and as the radiation hits it and diffuses, then this looks at that radiation, takes in IR here, and puts out visible to your eye. And obviously, please don't take this outside and look at the sun with it. You will damage the internal structure. And you should at this time develop some good sense of being careful with optics, because everything is expensive. It may look like nothing, but it costs a lot, and it requires care to be useful to you. Otherwise, you'll get scattered light, you'll get thumbprints on things. This is worth on the order of $20,000 if we had to replace it. So don't just go randomly turning the knobs wondering what they do. Please read the manual and then go ask the instructor before you go any further. Now, for this experiment, it's important to know what characteristics this radiation has. So we need to know what the wavelength is, and we need to know what the wavelength spread is, because it's not perfectly monochromatic. We want to know something about the power which comes out about it. And the question is, how are we going to measure these things? Well, some of it is easy to answer. Some of it, we can take a frequency meter. This is nothing but a diffraction grating spectrometer, all set up to measure wavelengths in this region. So you just put it up there, it turns out a number, and that's the wavelength, or you can translate it into a frequency. Another property of this is that it scans. In other words, the frequency is not fixed exactly at 780. By adjusting some parameters inside, you can change the frequency or the wavelength at which it operates. So it is variable, and there's a range over which we can tune it. And as you tune it, the frequency meter will measure it, but sometimes we need to tune it to a finer degree than the frequency meter itself can tell us. Doesn't have enough resolution, we say. And so we need another instrument, and that one is going to be called a spectrum analyzer. And that's just another fancy name for what we call a Fabry-Perot interferometer, or often called just FP. So this will measure the wavelength pretty well. If you want to, we can tune it. You want to measure the accuracy of how much you're doing it, we need the Fabry-Perot interferometer. And since that's the first part of our experiment, measurements with an interferometer to see how it works, let me discuss a little bit now what an interferometer is and how it works. Because you can't take these instruments apart and look on the inside. You do that, you destroy it. So let's have a little tutorial session on the Fabry-Perot interferometer. It goes like this. We have two reflecting surfaces that are not totally reflecting. Just for the sake of talking about it, let's say that the amount of light reflected is about 0.9. Or if I send light through here like this, about 90% of it will be reflected at this surface, and 10% will get through and reach the second surface. And then of that 10%, 90% of it is reflected, and we get then nominally 1% from what started in it. Now you might think, well, what's the use of that? Well, the use of that is simply this. I will say we put light up here as a wave front rather than a single ray. And because of this reflectance, now I'm going to neglect some parts of the reflectance and speak of parts of the other, and I'm going to expand it so it looks like that. And I'm going to use a little bit of an angle so you can see what we're doing. As the light comes in like this, most of it will be reflected. As it comes in here, some more will be reflected like this. But it gets reflected there, and it comes back again, and more comes out. And I'm exaggerating this angle. It goes like this until we get multiple reflections. Now each time the reflection is getting weaker and weaker and weaker and weaker. But nevertheless, they produce some very special things here. When this path difference is a multiple of a wavelength, then these are all in phase when they come out. And if I put a lens here like this and bring them together into a place like this, there will be an interference there. And if they add up all together, this will be an extraordinarily bright spot. And it's so bright that it looks as if there was no reflectance here at all. It just comes straight through. You have to take my word for it unless you want to go do the mathematics. If, however, this thickness here, this spacer thickness, is just right, then I can have at this point all the light canceling. In other words, if I move along a direction this way, I will get spots where it is maximum, minimum, maximum, minimum, maximum. And this looks like we have, if I rotate it about this axis, a system of rings, bright rings. And if I try to draw a little in perspective, that would be a spot, this would be a ring, this would be another ring, and those are called fringes. And if I were to take these plates and move them slowly farther and farther apart, these rings would gradually get collapsed down into the center and move and disappear. And there is an equation that describes the position of these wings. If there's a line through here like that, and we call it an angle theta, then if we say m times the wavelength is 2t cosine theta. Now, you'll have to study this a little bit, but this says that if this is an integer, that's how many wavelengths in going back and forth from two successive beams. In other words, one beam comes through here, one goes through here. They differ by this much in distance. If they're an integral number of wavelengths, then you get a maximum. And this explains then, if you pick a fixed m, as cosine theta changes, then we're going to, if at a particular cosine theta, we get a particular wavelength. So here we are with our laser, a system of rings. Now, I will even do a little more than that. I will put in an aperture here, a little hole, like this. And I will put a detector here, not my eye, but an electronic detector, electric detector right here. And then as you change the spacing, this goes from bright to dark, depending on interference, and you can then measure the wavelength because you can measure the thickness. Or, in our present experiment, if I want to scan over a range of wavelengths, I'll move this apart, back and forth, and I will scan what wavelength gets through here. And this allows us to measure wavelengths that are very close together. This, for example, it can be on anywhere from a fraction of a millimeter to many centimeters, and that relates to how sharp the lines are and what happens here. The whole point is that a Fabry-Perot, which is called a spectrum analyzer, is two reflecting plates that are scanned back and forth, and that changes the frequency or wavelength of the light that's allowed to pass through it. And if it's not the right wavelength, it will cancel itself and not go through. So it allows us to measure very small changes in wavelength accurately. So the ballpark with the frequency meter, commercially bought, that's it. Really accurate, small wavelength changes, a scanning Fabry-Perot interferometer. It's worth reading up in the reprints about this, and I should point out that I have just picked two plain parallel plates, whereas in actuality they are reflectors, they are concave reflectors, and it increases this effective distance, which we can talk about sometime at leisure, or you can read about them and how this has changed. This could be a 4, it could be a 6, it could be an 8, so 2, 4, 8 without any problem. So we're going to use that. What does it actually look like? In a few minutes we will go look at it. It's about as big as your thumb. There's a mirror here and a mirror here, and a piezoelectric device to scan it if you put a sawtooth of voltage on it, and that's all the bigger it is. And yet it allows us to measure the wavelength of a light to a very, very fine degree. This frequency meter, by the way, which is not as accurate as the Fabry-Perot interferometer, this is actually built in to the laser itself. It is not a separate instrument. So let me show you now how we're going to set an experiment up just to measure the properties of this spectrum analyzer, this Fabry-Perot interferometer. And perhaps before I do that, I should say we have several ways of expressing wavelengths, frequencies, distances. And let me just give you a little bit of background on this. You know that any wave motion, the frequency times the wavelength is the speed of light if we're looking at light. Any other motion, it's just the whatever the speed of it is. So we have several things we can measure here. This is measured with respect to time. And you know that visible radiation has a frequency of something like 10 to the 14th or 10 to the 15th hertz. And it's pretty hard to measure that high a frequency. We really don't have anything that can go that way. This one is a distance, and we can look at that in the following way. If this is a sinusoidal wave that's traveling with a speed c, the wavelength is just the distance between these two peaks. And we can put it here. But there's yet another way to look at this. We can say, suppose I take a standard distance like this. How many wavelengths appear in this distance? That is a spatial frequency. And so we have another number, sigma, which is the reciprocal of the wavelength. To repeat, the wavelength is the difference between two peaks. In time, it is how much time it takes to go from here to here at the speed of light. The wave number is the reciprocal of the wavelength, and that's how many waves per centimeter. And we use all three of those interchangeably, even though we probably shouldn't do it. But nevertheless, you will see those units. And we think of it, what do we say? When we have some kind of small radiation, small frequency, high frequency, however you look at it, that's in megahertz. But the wavelength can be in nanometers, or it can be in reciprocal centimeters. And all of these have an equivalence. And they're all connected by this wavelength. So I'll leave it to you to sort those out, but let me show you the first experiment we're going to do and what results we expect to get. The first experiment we're going to do is getting used to using the spectrum analyzer, the Fabry-Perot interferometer. We will have the diode laser here, almost a little bigger than that, and we'll make the radiation come out like this. Then we will split off a piece of that radiation with a partially reflecting mirror like this and send the beam here. Other experiments go on down here on the setup table, and we will put here, however, our Fabry-Perot interferometer spectrum analyzer, and we will put a detector over here. And we set this up now with a fixed wavelength, and we scan this. And you remember we had the equation m lambda is 2t cosine theta. Now we're going to have a small hole through which the radiation goes right here, so effectively the cosine theta is 1. And we do this, and we vary t by scanning a piezoelectric crystal which moves one of the plates of the interferometer to change the spacing. And to that we put then the scanning, it's a scan, not a scam. The scan, the voltage onto the piezoelectric crystal just goes like this. And so we scan a certain distance above some average value. And then the output is going to look like this. This is the amount of light we get out, and this will be the position or the scan or the time. We could make it several different units. And we would get, when this is satisfied, then we get a thing like this, and that would be at the order number m. We keep scanning a little more, we increase the voltage, the piezoelectric crystal gets a little bigger, and we come up to effectively to the next one. It's as if this pattern just starts moving out like that, and so we display in time something like this. Now you can see, you can plot it this way, backwards, time, distance, but this is effectively what we're after, and this distance right here is what's called the free spectral range. And our display, unfortunately, is not like this. We just turn it upside down in the actual display that we get, and instead of that way, it goes this way. And effectively what we say is that as we can either think of this changing thickness here with a piezoelectric crystal as either changing m or lambda. Either way. So we can say this is what you'd look like for the same wavelength. If you changed instead the diode laser wavelength, this would be lambda sub m, or lambda sub 1, lambda 2, lambda 3. So we can think of this change in distance as producing either a change in order or a change in wavelength, and we can use them interchangeably. So if I were to see another line in here, let's say something like this, we could say that's a different wavelength. And if we do see lines like that, we're in troubles because the laser is mode hopping, as is described in the experimental write-up, and is a bad sign. So in a sense, while you're learning to use this and getting familiar with the electronics, this is a diagnostic tool to say, is the laser working properly? And if it is, you should see on the screen, you should see in this in one of the rectangles, you should see this in one of the others. The next experiment is a little different. Let me erase parts of this and show you what comes next. We will put in another beam splitter and take off some more light and do another experiment. This time we're going to have a cell like this with a gas in it, and it's going to be rubidium. Now let's talk a little bit about what we might expect here in this particular case. We have to talk about the effects of sending radiation onto a molecule, an atom. What does it do with it? So I need to take a little detour, a little bit of a detour, and talk about some physics of absorption. And it goes like this. If we have a cell like this, and there are energy levels of an atom or a molecule here. I'll just take two of them, and we send light in here. This is the photon, h nu, if we like to think about it. And if we have two levels, E1 and E2, and if the photon wavelength energy exactly matches that, in other words, if E is E2 minus E1, then as the radiation comes in, it will cause a transition in this atom from here to here. And the light will not get over here. So if I put my eye here, and if there's only one atom and one photon comes in and it gets absorbed, then I'll see nothing. And if it's filled, if this is filled with many atoms and radiation is coming in, not everyone will be struck by a photon and absorb it, and I will see some light. So that if I were to say, well, scan this frequency here, scan this energy, then we could make a plot of the amount of light getting through versus the frequency of the scanning light that comes in. And when we hit this exact amount, like that, it would go like that, where this frequency is E2 minus E1 over H. And this would be an absorption spectrum. Well, that's what we could do here. We could put our eye here and get an absorption spectrum. What happens to this radiation as it gets absorbed here? Eventually, it comes back down again. We wait an amount of time, and it comes back down, and we get h nu again. But the difference is, whereas this is coming in one direction, goes straight through, but when it gets excited and then re-emits, it can come, and I'll just schematically say it goes in all directions. Here it's collimated, it goes in a beam. Here it's in all directions, and that's why you don't see it here. Now, the interesting about this thing about this experiment is some of this light, let's say, which goes in all directions, some of it comes out down here in this direction. And this is called fluorescent light. And you can say laser-induced fluorescence because we have a laser beam coming in now, and it causes these transitions, and we look at the light coming out the side, laser-induced fluorescence, and we then make measurements on this radiation. In our particular experiment, we have rubidium in here as a gas. And if we look at that, rubidium has several energy levels, and so we see transitions corresponding to very many of them. If we take, as an example, rubidium 87, it has energy levels like this. This is one designated doublet S1/2. It has another state up here, doublet P1/2, and a third state, doublet P3/2. If you don't remember your quantum mechanics, this is a good time to go review it and see what all these symbols mean. In our present experiment, we get rid of this one with a filter. So we just have two possible levels. We get rid of that energy. Now, there's also a nuclear spin, and this is equal to 3/2. And that effectively means that this level splits like this into 1 and 2. And this one is split. I need some more. Into 3, 2, 1, and 0. That's called the total energy, including nuclear spin. Quantum number is F. And we can have several transitions here that we make with the incoming light. There is a selection rule. This 1 can go to 0, 1, and 2. And the 2 can go to 1, 2, and 3, and I run off the board with it. So what we should be able to see when we scan this, and it's going to be scanned in wavelength, we are going to see these 6 transitions as spectrum lines. Now, what influences this? Well, you see here, we're scanning the Fabry-Perot, we're getting the spectrum of it as an analyzer. Here now, we're scanning the laser itself, the wavelength, we're going to scan over these frequencies, and you can arrange them. And if this is not familiar to you, then we need to go back, and I would say I'm not going to do them in any detail, but there's 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. You get all those, and you see a spectrum. They will be upside down, actually, this way, like that. But you don't want to let that bother you. So what we have done now is to make a good measurement. And if you want to know how accurately these are separated, what do? You go back to this experiment, which gave you a good wavelength scale in which to calibrate this scale. General frequency comes with the internal wave meter that measured the wavelength. But to make it very specific, you then can use the other to make this measurement. And you'll see it's extremely accurate. And in this particular case, instead of putting this in nanometers, it's often done in megahertz. But that's something you'll have to learn to live with. Let's look at some finer details of this experiment, because there are still more things we can learn. In our present setup, we exclude some of these lines. Let me just focus on the ones that we have and talk about that in more detail. These diagrams are correct. Whoop. These diagrams are correct. This was 3, 2, 1, 0, 2, 1. we're going to, for practical purposes, not use the light radiation that comes up from this level. We just exclude it arbitrarily with the filter. And we're going to concentrate on this one, which goes to here, and to here. And we're going to concentrate still more on it and look at it like this. And I'm going to draw it a little bit differently. If this is the wavelength and this is the amount of radiation, I'm going to spread it out. And you would find out that as you scan, the line shapes look something like this. And we are able to measure this very accurately, but we can't pick the peak accurately because this is so wide. What we would like to do is find some way of narrowing this. Now this is wide simply because this cell is full of atoms at room temperature. And kT for room temperature is about a 40th of an electron volt. And so effectively the atoms that are coming perpendicular are the true frequency here. The atoms that are coming toward us are on one side. The atoms that are coming away from us are on the other side. It's a Doppler effect that produces such a broad spectral line. And we would like to find a way of getting rid of that Doppler effect. We ought to trick the atom into thinking it's standing still. It's cleverer than you might think. What we do is take another split of radiation here. This time we're going to put another split like this, and let me temporarily erase some of these things so I have a little room to operate in. And we send it by means of a mirror up here like this, back down through here, and I'm going to put a detector right here, and a mirror here, and a mirror here. Now what have we done to it? Well, we have put two passes of the light. It's the same radiation wavelength. One goes straight down the middle, and one goes back through it here. So in this point we have two beams, one going one direction, one going the other direction. So they're counter-propagating beams of the same frequency. And you ask yourself, so what will this do? What will this do to our experiment? And by the way, this one beam is just blocked off. It doesn't go anywhere and is stopped. Now we have to reorient ourselves, and this is a little harder, and it will take a fair amount of study on your part to see what's going to happen. And the reorientation comes about because of this. We say, what about the population of the, let me turn it around. These represent effective energies of the atoms in the cell. And this can be said, well, that's the number of atoms at any particular wavelength, because they're moving, and so the wavelength we would see them radiate is different from if they were standing still. If we detune the laser a little bit from the center, and let's say put the laser frequency here of the one that's going through like this, the other beam is going the other way. And so its frequency is the mirror image of that here, like that. So when you talk about the number of atoms that you're going to see in the population, this represents the number that are available to use for observation. These don't come in because they've been absorbed by the atoms moving with the proper velocities in one direction, and so it has taken atoms out of that energy state. They're excited now, and when they re-radiate, essentially the radiation is lost. So we effectively have two things just like this. Two holes. They're not real holes, but they're decreased in population because they've absorbed radiation and gone somewhere else. What if now we start to scan the laser? If we scan closer to the middle, it will move that up to here and this up to here, and you keep scanning like that, and pretty soon it hits here. Now it goes down twice as far because you've got two beams like that operating on the same atoms, because those are really different samples. So in effect, when we scan and when we hit the center, then these are the numbers of atoms that are available, and we have produced a minimum. But the important part is it's a very sharp spectrum line. So when you hit this, when there's a drastic change in light that gets through by this analyzer, this is called the probe beam, then it's going to make a dramatic difference in the intensity, and you say, aha, that's the exact frequency, and we can determine it with a half-width of that, which is many, many, many times smaller than this one. And this is called Doppler-free saturated absorption. Saturation simply means you're taking the atoms away. They don't exist anymore to use. And this is the second part of the experiment to make the measurements that give you that. The next part of the experiment follows what we have just done. The problem is it requires a more sophisticated view of light and polarization of light. So what I want to do is talk a little bit about polarized light and how it operates and works and is characterized, and then go on and do the third experiment. We just put another beam splitter in and go here, but I'm going to erase this and talk about some physics of light first before we do that. But just keep in mind it's the same basic setup. We just tapped off the light for another experiment. Now everybody here, I think, has heard of polarized light. And Land, the Land camera person who made his fortune in Polaroid, is one of the big contributors to the field. So I want to say what polarized light is. You recall that light that you see from, let's say, the sun or this fluorescent lamp up here is said to be unpolarized. And that simply means that the electric field is in a direction in space that is random. And if you averaged over a long time, the directions would go out to be zero. You remember that if we use E cross H is S, the pointing vector, you know that E and H and S are perpendicular to one another. And this has a particular direction in space. But let's say if I look at the light here for a small fraction, a millionth of a second, this electric field, let's say, would be this way, then it would be this way, this way, this way, randomly, so it would go all every direction. But if I had some particular device that would make it always go this direction, just take the components of all the others, put them all together, that's linearly polarized light. So if you say light goes along this direction, and if the electric field is up here all the time, it's oscillating with the frequency of light, but if it's like that as it propagates, that's linearly polarized. And we can say if it's propagating in the z direction, then the polarization must be in the xy plane. And if I have a polarizer, then I can make it pick out any one of these and polarize it in any direction so long as it's in the xy plane. So we have what's called then linearly polarized light. But what if I had something like this? We have this E cross H. Suppose the electric field has two components. Suppose as a vector it has an E in the x component and E in the y direction. Well, there's no problem there. But now let's talk about a phase. Suppose all of these have the same phase. Then you could say, well, I'll call this EY and this EX, and so then with the same phase there would be E, and it would have a larger value, but it would still be polarized at 45 degrees, let's say here, to the y-axis. But what if you changed the phase? Suppose that in these two things, this one has a phase angle here, and let's make it pi over 2, 90 degrees. Then what we have is one vector in the y direction going up and down like this, and this one out of phase by 90 degrees. And what happens to you? Well, it shouldn't take you much effort to see that here we go is the electric field here, and it's rotating around here with the speed or frequency of the light that's going there. and this is circularly polarized light. And, you know, if you put up a filter that said, I'll measure EX, you'd get EX. You measure EY, you get EY. And it's very hard sometimes to visualize this because you don't stop and think. We don't see light and its phase. We know it's there, but we don't see it because we don't have anything that will respond that fast. 10 to the 15th hertz, that's on the order of atomic frequencies. And so we do the square root, the RMS value, in order to get the light itself. So we have to look for some means which will detect this, and we can do it by means of polarization and interference. There's something else here too. I wanted to remind you that the direction which this goes will depend upon whether it's this one that has the extra phase or this one that has the extra phase, which is leading, so to speak. You remember in AC circuits, current in an inductor lags the voltage, and in a capacitor it's the reverse. So we can also have polarized light that goes this way. Can your eye see the difference? No, your eye can't. But there are other things that do make a difference to you. All right? Now we have that down. Let's talk about properties of some crystals and what they do to us. Some crystals go like this. I'll call this a crystal with an axis to it. And by an axis, you can guess the structure is such that there's an axial, uniaxial, biaxial, whatever, but there's an axis to it. What if I send light onto this? And let's say I'll do it this way. Suppose we take light polarized in the y direction ahead like this. Well, there are certain crystals that'll just go right through there and not see a thing. Now, Ed Land, the Polaroid man, he discovered that if you took light that was perpendicular to this, it wouldn't go through the crystal. He found certain crystals that did that. It was known before him, but he's the one who learned how to use it. And so what happens if I put unpolarized light here? It gets polarized, and only this polarization goes through. If I turn it like that, then only this polarization goes through. What if I turn it in the middle? Well, that's not hard. You all know how to do vector analysis. So in comes this vector like this, and one component is along this axis, and one is perpendicular, and the one perpendicular to the axis goes right through, and one along the axis doesn't. So you get a difference. You get a polarized light at an angle, like this. But now there's a still better one. Suppose this is very thin. And suppose it has an axis, but it doesn't absorb the other light. Let's say it's a lossless crystal. Then what happens when light comes in at an angle? You get part of it going through this way, part of it this way, and they add together when they get through, and you get linearly polarized or elliptically polarized light out the back, depending upon the difference in path length. You say, difference in path length, what's that? Well, you know that the difference in path length depends on the index of refraction. And when you have a crystal, the index of refraction is different for different directions of the electric field. So now we have two components. We have a device which changes the plane of polarization. Now, let me give you even a more bizarre thing that happens. Let's suppose this were quartz. Quartz is called optically active. And that says that when you have a beam of light strike this at other than one of the axes, it splits it into two components, just as the other crystals, but they are circular polarized components instead of linearly polarized. So what happens is, inside the crystal you have circularly polarized light. When it comes out again in the air or vacuum, it changes back again. But you can't characterize its effects without saying that the crystal quartz splits linear polarization into two, makes them circularly polarized while they propagate in the crystal with different indices, and combine to give linear polarization when you get through the crystal. It's a concept backed up by the mathematics. You can write the equation in the vector notation, you can make it in tensor notation, and you can account for all these things and why you have to have these points of view. So what we're going to do now in an experiment is to take light, polarized light, put it on a crystal that has an axis that changes it to circularly polarized light, and see by how much it affects it when it passes through the substance. And we're going to get that by using magnetic fields. So just keep this in mind. What we will do then is have along come light that's linearly polarized. It strikes a material that changes the polarization going through because it changes the speed of circularly polarized light, recombines it out here. So we're going to measure the difference in polarization from one end of this medium to the other end of the medium, and we're going to measure how strong that difference in index is by measuring how much magnetic field we put on for a given rotation of the light. And there's where we get magneto-optical rotation that we have here, and that's the basis for this experiment. In other words, artificially we make a substance optically active. Here's how the last part of the experiment is set up. We have our laser again right here. We have the radiation coming out. We have these other beam splitters. I put in another beam splitter like this and come down and go through the same cell or the equivalent cell of rubidium that we had before and look at it out here. Now we have to be very careful in making the alignment, but because we care directly about the direction of polarization. So we have to have a linear polarizer in here somewhere, and that will be here. And I'll just write linear polarizer. What is it? Well, Edwin Land, who did this, took some natural crystals, oriented them all in the same direction, pasted them on some plastic, and hold it up. And you know that as a Polaroid film, which is a linear polarizer. Actually, there are two here because we want to adjust the amount of light to be just so. Not too much, not too bright, not too weak. And if we have two polarizers that are linear and turn them at an angle, we can go from max light to zero light. So this is really an intensity adjuster and a polarizer adjuster. So we have to have something either in here or, more directly, a very good linear polarizer to make the light exactly polarized. The quality of these is all important because we need another equivalent polarizer over here and what we are going to measure is the difference in polarization from when it enters the cell to when it leaves the cell. And you say, well, how much? Well, that depends on how big a field you put on it, because you need a coil and a current in the coil to put a magnetic field along the axis. And the greater the field, the larger the change in polarization. And there is an equation that people use for this thing. It just says that theta is some constant times the magnetic field times the length, like that. And this has a name, it's Verday's constant. And in a particular experiment that's going to be done here, or usually done without any nonlinear things, this is on the order of a few degrees. And of course, the part of the experiment is nonlinear, where that can get to be very large near a resonance. You can get the rest of that out of the experimental write-up. But this setup is crucial to it, just like this. And it just consists in taking the data and finding a constant, and a little more than that too. And remember, this is rubidium. It has a resonant frequency. You can tune the laser until the laser frequency is exactly on a resonant frequency in rubidium. And you can also tune it off resonance a little bit and make the same measurements. And you'll find some very interesting things. In a nutshell, this is the magneto-optical experiment. All the equipment for this experiment is contained in this curtained box. And it might be appropriate to mention a few things about optical elements. You'll notice that everything here except this package is optics. Optics is meant to be seen and neither touched nor breathed on. You know how if you drive your car for a long distance with the windows up, you get a little greasy film on the windows? That happens to optics. It's in your breath. So try to handle it as little as possible and breathe on it as little as possible. To help you remember that, we have it enclosed in this structure here with these side curtains and a fan on top blowing air into it through a filter, so that the air that comes down on here is cleaner and will preserve the optics, so we don't have to touch it or change it or clean it. If you should happen to touch something, don't try to wipe it. Go get an instructor. And that applies especially to things like the laser. As we go through the discussion, it might help if you get out the laboratory manual and look at this diagram. Everything in this diagram is here on the table, and it will help you follow it if you've looked at it already. Let's start with the laser itself. The laser itself is contained in this little box. It looks sturdy, but it has a few knobs on the outside. Please don't touch anything. This box and its associated electronics are worth $20,000, and it's very easy to damage them. The controller for the laser is right here, 2 pieces of electronics, and this package should be all adjusted when you come, and you shouldn't have to adjust anything. Just throw the switches and turn the knobs on these 2 boxes, and the radiation will automatically come out of this box here, pointing horizontally in that direction. The radiation itself is about 10 milliwatts at 780 nanometers. You may recall that 10 milliwatts is right at the threshold of permanent damage to the eye, so you don't want to look into that. But you can't see it because 780 is past the visible region of the spectrum, and therefore you need a way to look at it. And if you want to see the spot, we have 2 things you can use. The first is very simple-minded. It's just in a little folder here and consists of a square piece of sensitive paper. And all you have to do is let the beam fall on that little square, and it will become visible. And you can try that without any difficulty. All you would do is come down and put it here or here or here, and you could easily see the beam. If you get into a tight spot where you need something more accurate to locate the beam, we have a night vision telescope. A moonlight it's called, and it's really a monocular, and you just put it up to your eye. The on button is here, and you need to look at the beam reflected off of something, press the on button, and hold it down as long as you want to view it. The instrument is very sensitive to radiation, so you wouldn't look directly into the beam. But reflected off of something, you can see it quite easily. Now, the beam itself then comes out of the laser and goes through an aperture. This is just an iris diagram to adjust the size, how much light gets through. And then a series of beam splitters. Here, 1, and then there are 3 more along the line. We'll start with this one because the first experiment makes use of this beam splitter. A fraction of the light is reflected from here and goes into the next little instrument here, which is the Fabry-Perot interferometer. It's small, centimeter in diameter perhaps, and 2 or 3 centimeters long. You can read about it in the write-up and and in the references to see what's there. And this is the piezoelectric scanner, which scans the spectrum for you by changing the distance between the 2 etalon plates. And the electrical wire goes out to the general terminal box from which you can process it and put it on the monitor. And this part of the experiment, you simply connect it up, look at the fringes, scan with it, and get used to using this instrument as a spectrum analyzer. In the second experiment, we make use of the radiation which passes through this beam splitter and reaches the next two beam splitters, a pair which go together. These beam splitters take the light and send another fraction each down in that direction toward the cell. The first one goes through a rotating disc, a chopper, like that, which chops the radiation and allows us to use lock-in detection on a part of it. It goes through that directly to the cell here, which is about 5 centimeters in diameter and 6 to 8 centimeters long. It's a quartz cell filled with rubidium, the same as we use in optical pumping. And the light that goes from this first of the pair through the chopper, through the cell, goes to the background here, the black background, and is absorbed. We don't measure it directly. But the second beam splitter associated with this sends radiation in the same direction toward the cell, but bypasses the cell and hits the mirror back there. I see when it hits the mirror, you can see the cell lighten up in places because it's already coming back at us and coming toward us. And we see it scattered at the mirror surface, the window surface of our cell. So we have, again, from the first of this couple of beam splitters, chopper, cell, gone. The second of the two, bypass the cell, hit the mirror, come back this direction, hit this mirror, go to the detector, which is right here. So we measure how much radiation reaches us in that second beam. We call it a probe beam as we change the wavelength of the laser itself. So with this experiment, we can measure the hyperfine structure in the energy levels of rubidium. In some respects, it resembles the optical pumping experiment. It's the same atom because it has very nicely spaced energy levels that we can learn something from and illustrate still more things about physics. So those are two experiments, very good. I won't say easy, but they're simplistic and you can easily go through them and understand what's happening. We have the third part of the experiment, and the remaining radiation first goes through a lens because we want to keep the light focused as it gets farther away, now through a mirror rather than a beam splitter, and onto two polarizers. The first polarizer is just two pieces of Polaroid changed with an angle between the two axes. You remember, if you take two pieces of Polaroid and put the axes in the same direction, light will go right through it and be polarized. First one will polarize it, second one will pass it. But as you turn one with respect to the other, the amount of light getting through goes as the cosine squared of the angle. So I can adjust how much light gets through this part. And in your experiment, if you're saturating the detector or anything, we just adjust the amount of light by turning this little knob and adjusting the amount. To do the experiment itself, we have to have a precision polarizer to set exactly to within a fraction of a degree the direction of polarization. And that is provided by a wedged crystal polarizer here, right behind the two pieces of Polaroid material, which are in plastic. So that's a precision polarizer. The light next goes through this cylinder. And what's inside the cylinder? It is another rubidium cell, just like the one we've already spoken about. Something about 2 centimeters in diameter and 6 or 8 centimeters long, filled with rubidium vapor. But this experiment is going to work with a magnetic field effects on the structure of the rubidium energy levels. So we need to shield it from external fields. And this shield right here is made of a very special metal that short circuit, so to speak, external magnetic fields. So what we get on the inside, we have a coil wound inside of that shell, and we put current through the coil and make an axial magnetic field. So what we have is polarized light, linearly polarized light, going through a cell of rubidium which is immersed in an axial magnetic field. And the effect of that is to change the direction of polarization, and that is detected by another precision analyzer. It's just another polarizer, but you'll turn this at a slight angle to get the maximum amount of radiation through it. And that goes out the back and is processed electronically as before. So we can get a picture of magnetic field versus rotation of the electric vector in the radiation.